All right, everybody, welcome back. In this video, we're going to talk about concepts from section 5.2 of AP Calculus, Extreme Value Theorem, Global versus Local Extrema, and critical points. All right, so we learned the Extreme Value Theorem a while back, but we're going to just start by revisiting it to refresh everyone's memory as far as what it says and what the scenarios are. Because we're going to utilize it in today's lesson. So the extreme value theorem says that if f is continuous on a closed interval, then f has both a minimum value and a maximum value in this interval. So if I have this function that is continuous on a closed interval, like this one, okay, it has, you'll note, both a maximum value, there's the maximum value, and it has a minimum value somewhere on that interval. And that's guaranteed if a function is continuous. If a function is not continuous, it could happen. I could have a maximum value or a minimum value or both, but they are not guaranteed. For instance, here's an example of a continuous function, or pardon me, of a discontinuous function, where it has neither a maximum nor a minimum value on the interval. Now, of course, we could have a function that was not continuous that did have a maximum or minimum value. I'll draw another one in green here. Suppose I have this function here that's discontinuous, but it still does have maximas and minimas. Okay, the thing is if it's not continuous, it's not guaranteed. All right. Brief side note, talked about the mean value theorem and the intermediate value theorem. These two theorems, along with the extreme value theorem, they all have the word value in common between them. These are all known as what are called existence theorems. They are guaranteeing the existence of a value that meets a certain characteristic. All of them are going to come up on your AP exam. It's important that you know what's required for each and the conclusion that follows from each of them. So those are three big important theorems. If we give a theorem a name, chances are it's pretty important and you're going to want to know that theorem and what its hypotheses are and what its conclusion is. Okay, definition here for what are known as absolute or global extreme values. We'll use those two words interchangeably. Sometimes we call them absolute, sometimes we call them global. You'll see those two words used to represent this situation. Depending on where you look, you could see either of those words representing this situation. So what are absolute extreme values? If we have a function with a given domain, then the value f of c is the absolute maximum value if and only if the function is less than or equal to f of c for all x in the domain. So if we have a value that's bigger than or equal to all other values in the domain, then it's the absolute maximum. It's the biggest of them all. Same thing for an absolute minimum, only reverse conditions. It's an absolute minimum value if and only if the function is greater than or equal to f of c for all values of x in the domain. And I rephrase that down there below. Okay, so that's one type of extreme value, the absolute / global maximum and minimum. We also have what are known as local or relative extreme values. Okay, these are extreme values, but they're not quite as I want to say they're not quite as extreme as the it sounds like a Mountain Dew commercial. They're not quite as extreme as the absolute or global extreme values. They are bigger than everything that's close to them. So the way we define local or relative extreme values, a local maximum exists if and only if the function is less than or equal to that value. And then instead of being for all x in the domain of the function, it's for all x in some open interval containing c. And as long as I can build an open interval where the value of the function is greater than all the other values of the function around it, then we consider it a local maximum value. Sometimes we refer to these as the values in its neighborhood. Is a different way of us saying this. Similar statement for local minimum value at C, if and only if f of x is greater than or equal to f of c, again, for all x in some open interval containing C. So we look at this picture, and there's something that's not filled in here that should be filled in. This should also be considered a relative minimum. Something that we will say is all absolute maxima must also be considered relative maxima, and all absolute minima must be considered relative minima, but not vice versa. If we have an absolute max, it must be considered a relative max. If we have a relative max, it does not necessarily have to be the absolute max. Think about it this way. If you're talking about an absolute maximum, it's bigger than all values of the function in the domain. And a relative max is bigger than all functions in some interval containing C. Well, if something's bigger than all values in the domain, then it has to be bigger than all values in any open interval around it as well. So if it's an absolute extreme, it must also be considered a relative extreme, but not vice versa. And you can see some on this picture. We've got the absolute min indicated, the absolute and relative max indicated over here, and then some other, a relative min here, a relative min here, and a relative max here. And what I can do is I can set up an open interval around B here, where the value of the function right here is greater than or equal to the value of the function for all values in that open interval. It's bigger than all of these values around it and nearby it, even though it's not bigger than this value over here. It's bigger than everything in its neighborhood. And as long as I can put some kind of open interval around it where it's bigger than all the values in that open interval, then it's considered a relative extreme. All right, let's take a look at example 2. We're going to find some extreme values on these graphs. We're going to identify the type and where they occur. Okay, first of all, I have a local and global min. Of positive 1 at x equals negative 3, this value right here. It is smaller than all other values of the function on the domain of the function, and it's also smaller than all values that are close to it. And when we have an endpoint of a closed interval, that's always going to be considered either a local max or a local min, because I can always extend an open interval away from it where it is either bigger than everything around it or smaller than everything around it. All right, let's see what else we've got here. We've got a local and global max. I'm just moving left to right. Of 5. That happens at x equals 0. There's the maximum value. The function is bigger there than it is anywhere else in the domain. All right. Right here, we have a local min. A local min of 2 at x equals 1, because right there the function is smaller than all the function values around it. Like I can make this open interval right here, and every function value in that interval is bigger than the function value here, which makes that a local min. And then over on the right end, we have an open endpoint. Okay, so we technically do not have a local max there at that endpoint because the endpoint's not included. If the endpoint were included, then we would have a local max of about 2.8-ish at x equals 4. But we do not have a local max there because it's an open endpoint. All right. All right, part B, go through the same way. The left endpoint here, we do not have, again, we have an open endpoint there, so we do not have any kind of extrema at this open endpoint. Right here at -1, we have the local and global max of 3 at x equals -1. And then at at 1, we do not have a min there. We don't have a global min either. And notice the extreme value theorem does not hold for us in either of these two examples because they are not continuous functions on their domain. So we're not guaranteed to have a local and global, or we're not guaranteed to have a global max and min. In example A, we do. In example B, we only have a global max. We do not have a global min. All right. We do have a local max of 1. At x equals 1, right here. That's bigger than all the values of the function in some open interval around it. And we have a local min right over here of -1 at x equals 4. Okay, so there are our local and global max and min. Let's see, do I have enough time to finish this? No, probably not. All right, so we're going to wrap up this video here, and we're going to come back with a very short, or a shorter video for the second part of this lesson on the extreme value theorem and global versus local, extreme, and critical points. We're going to mostly talk about critical points in that video. All right, I'll see you then. Have a great rest of your day.